So hello everybody, and thank you for joining me to watch the first lecture on our course in solid state physics. And I would like to first just introduce the general table of contents for the whole course, because I hope that motivates our first chapter that focuses on crystalline structures, like what are periodic structures, how do we define them mathematically, and then outline the first bits and pieces of physics regarding solid state physics. And after the first chapter, we have then constructed the necessary mathematical formulations that we can understand what are periodic structures. And when we know that, and when we know that it's actually the periodicity of solid form, solid state, that dictates quite a lot of the properties of the solid piece of a material, that acts as a good motivation for the rest of the chapters and topics we're dealing in our course. So for example, in chapter 2, which focuses on bonding in solids, it's very much connected, because here in chapter 2, we're kind of trying to look superficially though, but nevertheless, we try to look and understand what are the microscopic physical principles, the forces that play a role in formation of different crystals. And after that, in chapter 3, we focus on the mechanical properties, and then there we also learn that it's actually the crystallinity of a material that matters quite a bit. And then we want to understand and be able to at least like rudimentary answer questions such as that what kind of shapes, what gives rise to the rigidity of a material, why some materials are malleable, for example metals, that we can hammer them down into different shapes, why some other materials are brittle so that they fracture relatively easily, and what happens in between. And here in mechanical properties, we don't mention it much, but we learn that this atomic lattice structure that is like underneath the solid, the crystalline structure, also matters in thermal properties of the lattice. So there's like a small atomic vibrations that are created or can be created because of the periodicity of the system. And those atomic vibrations, lattice vibrations known as phonons, they also affect the thermal properties of the lattice. So thermal properties of the material, like what is the heat capacity of the material, how well it can conduct heat, and how much it can absorb heat while changing its temperature. And then we go to the electronic properties of solids. So then we are more focusing on what happens for electrons, quantum mechanically speaking, inside a piece of a solid. And here we learn that it's absolutely necessary to understand what is the periodicity of the structures. And then we go to yet another different class of a material, so semiconductors, and we outline the basic physics regarding them. And finally, in the last week or so, we speak a little bit about dielectric materials. And in here, we will also outline a bit of mathematics that helps us to understand how we could calculate the electronic properties of dielectric materials. So we introduce to you a slightly different mathematical way to calculate and estimate what kind of energies we may have in dielectric materials, what kind of states our electrons may have. And the finite solids chapter, the 8th chapter, is more like a kind of recap of the things that we have already learned during the course. So I just wanted to say in the very, very beginning that it may not be visible to you when you're first time encountering these different chapters and topics, but after you have become more familiar, and if you would read the material second time or listen to me, maybe some things would start clicking more, and you would realize that these crystal structures, for example, as a chapter, it's very important to understand also the rest of the things. So this is the kind of logical starting point, and this is also very important. So that's what I wanted to say here right in the beginning of the course. And I hope you enjoyed it. This is super cool material that we are dealing with here. Solid state physics, even though it might have a reputation that it's like very terrible bit of physics, and very hard to understand. It's actually very interesting once you get past the first barrier and you start remembering the concepts, terminology, and the main simple pieces of mathematics that we're dealing with here. And once you handle them well enough, then things become more and more rewarding because you're really starting to understand what's happening. And you start forming an intuition. So you start understanding things from the physical point of view. And needless to say, but solid state physics and condensed matter, which is a bigger a part of physics, it's actually very broad in scope. So I guess one could say that the half of the physicists around there in the globe are somehow dealing with solid state physics or condensed matter physics, broadly speaking. So it's a very large branch of physics. But let's now go to the actual topic at hand. So we will be dealing in the first chapter, crystalline structures. And in the very beginning, what is the point? What is the topic of this lecture? 1.1, we are outlining the simple mathematical formulation. How can we understand periodic structures? That is crystal structures. And after that, we go to the other chapters. But let's now start with our first chapter. So we will learn how crystalline, in other words, a periodic solid structures can be mathematically described. And basically then we learn how we can mathematically describe a situation where the atoms in question are in a lattice, so in a periodic arrangement. And how do we treat such lattices mathematically? So we learn what are generating vectors. We learn what's a Bravais lattice or what are Bravais lattices. There's actually more of them than just a single, many types. What's a primitive lattice cell or just primitive cell in short, and what are primitive translation vectors, and what's a generating vector, what's a primitive generating vector, and how we can use them to form these primitive cells. And how these primitive cells, they actually form a volume when we are dealing with the three-dimensional periodic structures. And in general, that volume is in a shape of a parallelepiped. Then we speak of Wigner side cells, which is a one way of forming a primitive cell, and talk a little bit about the concepts of a lattice point. And especially I would like to outline this and highlight this, that please, from the beginning, distinguish between the concept of a lattice point and what's an atom in the lattice. So distinguish between the lattice point and what we actually put into this lattice point. Many times we think that this lattice point actually is equal to an atom, but that need not be the case depending on the actual solid. And that's where the complications then start emerging. And then finally, in this lecture, we will introduce to you the basis of the lattice and the different symmetries these lattices will or may not exhibit when we start forming more realistic materials. So that's what we will be learning today. And let's get started. So what we learn, and as I just mentioned, in this course, we really want to understand how solid matter behaves. So we want to understand the thermal properties. We want to understand the electronic properties of solid matter. And here, what we mean with solid, we mean periodic matter. So this is a course in solid state physics and not a course in condensed matter physics. Because in condensed matter physics, we could also be studying amorphous materials that are not periodic. For example, polymers and liquids and other forms of matter. But here we are focusing on periodic. And of course, I guess one could say that there's this something between entirely non-periodic structures and periodic structures. For example, quasicrystals are structures that have order, but they are nevertheless not periodic. But maybe during some parts of the course, we will discuss a little bit about the quasicrystals. A Nobel Prize was awarded to them, and from the X-ray diffraction point of view, they are extremely interesting because the diffraction patterns we get out of quasicrystals, it's mind-bogglingly different from what we get from normal materials. So there was a reason why a physics prize in Nobel Prize in Physics was awarded by the discoverers of quasicrystals. So in a nutshell, and graphically speaking, and this is what we will be dealing in this course. So we will have an atomic lattice, and we will put different kinds of stuff into the lattice points. So we put atoms, and more or less, I will just draw this kind of red and blue and green spheres into 3D lattice points. And depending on how do we put the lattice, how do we fill the lattice, what kind of atoms we put there, and where do we put them, then the actual properties, the macroscopic properties of the solid will change dramatically. And this is another picture roughly showing what kind of structures we are dealing with here, what kind of solids. So periodic solids. And as I promised, we will really start with the mathematical definition of the lattice. And Hoffman's book is saying things verbally, so that the lattice, and lattice is a word meaning it's a periodic arrangement of something. So a lattice is a set of regularly spaced points R, and that's our lattice vector R. And the positions are defined as multiples of generating vectors. So that's a piece of terminology here. So we have some kind of vectors that act as generators of this space. And the space is basically the collection of all the points R that may be formed accordingly. So in two-dimensional system, and this is the good place to start, R is given by a relation where R vector equals M, an integer times A1, a principal, or sorry, not a principal, but just a translation vector A1, and plus N times integer times A2, which is another translation vector. So since M and N are integers, we see, now we can put like zeros there, ones there, twos there, every integers we can imagine, and also negative valued ones. And that then we will get a space, a collection of points, capital R. And this is a way how do we define a lattice in two-dimensional case. In three-dimensional case, like this is a no-brainer, we see that the capital R can be written as a M times A1 plus N integer times A2 vector, a translation vector of the lattice, plus O, and another integer times A3, which is now the third translation vector. So this is the three-dimensional case. How do we write the R, capital R? So N, M, and O are integers, and the vectors AI are the generating vectors. And instead of I, we may put 1, 2, or 3 there. And in some cases, we could put, instead of 1, 2, and 3 sub-indices, we could just use labels X, Y, and Z corresponding to the Cartesian system, but that is not in general the case when we are dealing with different types of crystals. So that's why I prefer this notation where we're just using indices 1, 2, and 3 so that we can treat the most general of cases. It's also better when we are forming summations over the indices that when we have 1, 2, 3, like forming summations, the notation gets less clunky. So this is a figure that then shows what comes about when we are like forming a lattice forming out of the capital R lattice vector. So basically, depending on the integers M and N, we will form a different kind of lattice. And as you can see here, they like if this direction would correspond to the direction of A1 vector, the generating vector, and then if this direction here would be corresponding to the direction and length related to the second translation vector A2, we see that they do not need to be orthogonal in direction, so that they can be in oblique directions with respect to each other. And here, of course, the lengths of the vectors, they do not need to be equal, so that the different kinds of lattices can be formed. And this is the case for a 3D lattice. And then we have the 3 different translation vectors, A1, and they then generate the space that we have. So different when we put different integers M, N, and O, we get a set of points capital R, and that defines our space that we will be dealing with. So a lattice can basically be defined as all the points R that really are in there in that space. So one could say mathematically that this space, these points of R, is spanned by these translation vectors A1, A2, and an A3. So because of that, we could say that these A1s, A2s, and A3s, they are the generating vector of our space. And when we are generating a space, a collection of capital R points, or in other words, we are generating a lattice, a periodic arrangement of these atomic points, or just lattice points may be a better word here. This is called a Bravais lattice. So depending on how do we do, what are the generating vectors, some slightly different Bravais lattice configurations may be created, but all of them, these periodic lattices, they are called Bravais lattice. And when we can describe a lattice with this kind of a collection of points of R's, then we say that that's a Bravais lattice. So that's another piece of terminology here. So 14 different kinds of Bravais lattices exist, so that there are many, but on the other hand, not too many. And symmetry-wise, hell breaks loose when we start putting something different than just a singular points into these lattice points. But a word of that later. So what we do next here is that we have described how do we form a three-dimensional lattice. And next we define a primitive lattice cell, and verbosely put, this is also from Hoffman, a primitive cell. In short, we don't need to use the lattice there because it's obvious that when we are speaking of primitive cells that it's related to a periodic lattice. Any volume of space that when it's being translated through all the vectors of the Bravais lattice fills the space without overlap and without leaving any voids. So what that means is that we can really fill up the volume by just repeating these primitive cells, putting them side by side, and there won't be any voids. No space is left in between. So that it entirely fills this three-dimensional volume, this collection of different primitive cells. So that's what the verbal definition tries to say, and this is from Hoffman's book. Well, this is nice, and it works, it's accurate, but I think it's far better to try to understand things also mathematically. So let's now just go through the bits of pieces of mathematics, what this defines, this statement. So basically, we have the primitive translation vectors now. So we have AIs, and I'm using the word primitive here to describe that these are now giving rise to a primitive cell. So that we could also have slightly different translation vectors that would define the same space, but then the volume they would form would not necessarily be the primitive cell. So this, when we form a volume, a parallelepiped using primitive translation vectors AI, that is our smallest possible building block that we can imagine that forms the whole crystalline structure, the three-dimensional volume we were dealing here. And this volume can be formed by taking the cross product of the generating vectors of A2 and A3, and then taking a dot product with our a first translation vector. So this forms a parallelepiped, geometrically speaking. And this is how it looks like. And maybe it's good to kind of show slightly what this means geometrically. The triple product. So we may think first that we are calculating the cross product of A2 and A3, and we know that geometrically that's defining a plane that is being spanned by the vectors A2 and A3. And of course it's directional area, so it has a different given direction. And then we are taking the dot product of this entity with the A1 generating vector, and then we are actually forming the actual volume. And then it's an oriented plane that we get when we are taking the cross product, so that this entirely also defines the way the parallelepiped is being formed. So what is the handedness of the parallelepiped? But this is the case, and when we calculate this triple product, we get the volume out of this primitive cell. So this parallel pipette that is being formed due to this reason is called the primitive cell. And this is quite nice, mathematically speaking, because now it's enough for us to just know what are the translation vectors, and more precisely, what are the primitive translation vectors. And once we know them, we can form a primitive cell. And primitive cell is a very fundamental concept in solid state physics. So this sounds like a good and a useful bit of information for us. There are many ways to choose the primitive axis, and this is where complications arise. And this means that there are also many ways to choose the primitive cells. So we can draw slightly different primitive cells, and they can still be used as a tessellation of space. So that's a fancy mathematical word, which just means that we can fill space entirely without leaving any overlap and without leaving any voids. So that's what it means. But if you're interested in learning more, this is a very general bit of mathematics we're dealing with here. I recommend that you start reading from the Wikipedia article on tessellation of space and so forth. So that that's an often used concept, also like in architecture. Let's now get forward. What else is there to know about crystalline structures? So the number of atoms that we are dealing with here in the cell do not depend on the choices of the bases. And my apologies here. I'm saying atoms here, but I should really be saying that number of lattice points in the cell do not depend on the choice of bases. So when we have a primitive cell, there's always a single lattice point per cell. And be careful here, and I try to be systematic myself also during this lecture and during this course. When we are speaking of lattices, we should be careful that when we mean a lattice point, we just say a lattice point. And when we start populating these lattice points with different kind of physical creatures, then we should kind of acknowledge what happens. So only a single lattice point per primitive cell exists. And we may, for example, put just a single atom into each of these lattice points. And in this case, in this primitive cell, we would have just a single atom inside. But that does not need to be the case, as we soon learn. We could also put 2 atoms per each atom, like a lattice point. And then we would in fact have two atoms inside this primitive cell. So a word of caution here. Lattice point is not an atom. And when we are asking how many lattice points we have inside a primitive cell, the answer is always 1. But when we are saying that, okay, when we have a slightly different structure, how many atoms we have inside the lattice point, inside the primitive cell, it might be something else than just 1, depending on the basis of the lattice. So in the edges of this volume, the points do not count as 1. So for example, here we have 8 corners, and we have roughly we have equally 1/8 lattice points in each of those corners. And when we multiply, we get unity, so this is okay. We only have a single lattice point per a primitive cell. And a commonly chosen primitive cell is known as a Wigner site cell. And graphically, in 2D, that's how a Wigner site cell look like. So we have the generating vectors, the primitive translation vectors of my lattice, A1 and A2, and I'm using them to form a primitive cell. But instead of having my lattice points in the corners, I'm translating this cell, and I'm ensuring that my lattice point is in the center of my primitive cell. And when I do this kind of construction, this cell is called, in fact, a Wigner sites cell. And in real space description of lattices, this is not that often used, But when we go to this infamous reciprocal space, where many students have lost during the decades and thousands of years solid-state physics has been taught in universities, like when we go into the reciprocal space, this Wigner side cell actually starts to be a very useful concept, because when we are describing functions, for example, when we are describing an electron wave function that corresponds to an electron in a periodic material, then it's very natural and very useful to describe that function in the reciprocal space notation and inside the Wigner side cell or in reciprocal space. But more of that later. But I just wanted to warn you that this is something that we will encounter later. It has a different word then, but nevertheless, like it's still a Wigner side cell. And why do we go there, and why do we go into these reciprocal spaces? Because it's useful. But don't worry, we will go there once we have grasped the first necessary pieces of information, knowledge, and then slowly we will also start understanding what happens in that concept. So, as students always ask that they would like to have examples, and it's a valid request to ask, because indeed examples help us to understand. I'm now showing you how do we generate a Wigner size cell, and we can actually use this kind of following procedure. For the sake of clarity, I'm just showing this for a two-dimensional case, but nevertheless, like the same principle and same procedure works also in 3D. Just a hell of a lot easier to graphically show what happens in 2D case. So I'm starting with the lattice, and this is my center point. I'm taking this lattice point, and I want to form a Wigner side cell surrounding this single point. And these are the other lattice points, the adjacent nearby lattice points. And I will start just forming a kind of intersections. So I'm taking the nearby lattice point. So I'm going from here to the nearest neighbors, and I'm going here. I'm drawing a line. I don't show it on this example, but I'm just drawing a line here because that's what we would need to do in 3D case. And then I'm drawing either a line perpendicular to this line, and this is adequate in 2D case. And if I would be in 3-dimensional lattice, I would actually now form a plane that then like intersects this line I'm drawing normally with respect to the line. So when I draw a line, I can then define a plane that is normal to this line, and then I can draw that into my lattice. And then I will take another lattice point nearby my point of interest. This time it's this one. I draw a line, and I draw a plane that is intersecting this line exactly midway between these two lattice points. And then I repeat this procedure to all of the lattice point, the nearby lattice points. I'm drawing a line between the two lattice points, and then I'm in the midway of this line. I'm drawing a plane that intersects this line. And then I'm repeating this procedure for all the points that we have. And now we are in a stage that we have actually formed in 2D case an area that is completely surrounded by these dotted lines. And in a 3-dimensional case, I would now have a volume that is entirely being surrounded, enclosed by the planes I have drawn. And now I have my Wigner side cell in here, inside this location. So now I have my lattice point, and it's in the center of my Wigner side cell, and I have enclosed it with lines here. And this is my primitive cell. And as you can see, we soon, very quickly, when we are dealing with periodic matter, and if it would be in 3D case, things would become even more complicated looking. We end up with the structures that are not nice, like cubics and rectangles anymore. And this is even more complicated when we think of a 3-dimensional structures. So that's why I guess solid state physics is conceptually not the easiest of branches of physics, because we will need to grasp things complicated shapes, geometrical shapes in 3 dimensions. But okay, we have this piece. So we have a primitive cell, and because it's a primitive cell, like we can use that to tessellate our space. So we can basically repeat this to the nearby lattice points, and when we put this primitive cell next to all of the lattice points, what we see is that this area that we're dealing with, because we're dealing with a 2-dimensional lattice, we are entirely filling it with our primitive cell. So this is what happens. And we would be entirely filling the volume if we would be considering 3-dimensional volumes. And this is what happens. And this is important, so that we don't have any overlap between the primitive cell, and we certainly do not have any voids. We don't have empty regions that we don't have the capabilities of extending into with our primitive cell. So this is how we form a Wigner-side cell. And let's now just ask you some questions so that you can verify have you grasped these concepts. So let's study an example lattice, and there we have different cells, and we have highlighted them in different colors like this. And I will just now ask you questions, and then hopefully you already know the answer. So the first question I want to ask is that what of these is a primitive cell? And now you can pause the video, and then you can answer the question. And I will now provide you the answer that the primitive cell is exactly like they are those smaller rectangles there, so that they this, for example, is a primitive cell, and this guy is a primitive cell because they are being generated with the primitives generating vectors, translation vectors. And this guy is not a primitive cell because we could also form a smaller cell. And if we would now start to tessellate this space with this kind of cell, there would actually be overlaps, because we could move this cell one nudge upwards, and we would be drawing a cell in this location I'm highlighting with my arrow, and then we would have overlap with the previous cell. And this is no good, because we want to avoid redundancy in our mathematical description. A second question obviously will be that which one of these primitive cells then is a Wigner-side cell? And I now recommend that you will pause the video, find the right answer, and then you will continue. And yes, we will now continue. And probably you noticed that the red color here agrees with the fact that this is a Wigner-side cell, and you are exactly right. This is the Wigner-side cell, because we have the lattice point at the center of the primitive cell and not in the edges. So this is how we can form lattices, and this is the difference between any primitive cell we can imagine and what's a Wigner-side cell. And we can now also understand what it means when I say that there's many ways of choosing the primitive cell. That there's also an infinitely many primitive cells when we would try going between these two different cases. So we could imagine that we would shift this primitive slightly towards the center point and over. And when we shift it slightly, we would still have another primitive cell, but it would not yet be a Wigner-side cell. And when we shift them even more so, and more so, and more so, we have different kinds of primitive cells. And when we have shifted this primitive cell to be exactly in the middle, we have the Wigner-side cell. And imagining this procedure that we are shifting the primitive cell a little bit, nudging it around inside our lattice, we can understand that the choice of a primitive cell is not unique. We actually may have many different ways of choosing it. Now, final thing we will cover during this lecture is that we will introduce to you the basis of the lattice. So basis is the thing that tells us what kind of atoms, what kind of molecules, what kind of physical objects we actually have inside our lattice point. So what kind of building blocks we use in the actual crystal. So this is what basis of the lattice means. So in essence, this is a graphical demonstration what happens. So on the left-hand side, we have the lattice. So we have the lattice points, those black dots there, and then we may populate them differently. So for example, I may put something resembling a hydrogen molecule there, and we will have a structure that is shown on the right-hand side. And this is now the kind of physical structure, and its properties will be dictated not only by the lattice, but only how we populate the lattice. So what is the basis of the lattice? So structure or form of the basis really defines, for example, the symmetries of the crystal, and this is the easiest thing to see mathematically here. And when we go into physics, then we realize that these symmetries also dictate the optical properties, the electronic properties, and the thermal properties of the lattice. So entirely the properties of the lattice. So depending on what we put inside the basis, we may have a different amount of mirror planes. So these are different kind of symmetry operations we may have on a lattice. So we have different mirror planes. We may have different rotational axes, and an inversion symmetry, we may lose it depending on what do we put inside the lattice. So this really affects strongly the macroscopic properties of the solid. How do we populate the lattice points? This is important because we know from real life that even though we only have 100 or so elements in our periodic table, we have thousands of different kinds of compounds, or I don't know, millions of compounds existing in the universe. So somehow this different, a number of compounds dramatically increases, and how come that happens, and how can we have so many different kind of properties in the different compounds? It originates from the fact that they even though they might be crystalline, and they might have a similar kind of crystalline lattice, so the same kind of Bravai lattice, so basically the same kind of order as shown in here, but depending on what do we actually put them inside, then the properties will be different. So this is actually important to know, and we will speak about this or show see the first time that this is important when we go later on into the X-ray diffraction technique and how do we understand diffraction patterns. So this is another picture showing more tangibly, hopefully, what this basis of lattice means. So the lattice symmetries depend also on the basis of the lattice. So the kind of basic symmetry properties are being dictated by the lattice, like what's the Bravai lattice, and then depending on what do we put inside the lattice points, then we may lose some of the symmetry properties. Some of the symmetry operations are not symmetry operations anymore, depending on the choice of the basis. So for example, mirror planes, rotations, and possible inversion symmetry, these are the symmetry properties that dictate the properties of the crystal, and they may be changed. They may vanish when we use something slightly less symmetric in our basis. So for example, as an example case, if I could imagine a line at the diagonal, and I could then draw a plane there, and that could act as a mirror symmetry operation, so that they kind of upper part triangle and the lower triangle would look exactly equal when we would perform a symmetry operation, mirror planing. Perform a mirror operation on the lattice. And in here, if you would try to do the same thing, we see that we lose this diagonal mirror plane as our symmetry operation. The same thing if I would imagine that I'm drawing a plane, a mirror plane at the center, and if I would make a mirror operation, the different parts of the structure are not anymore symmetric. Here I will still have the symmetry when I draw a vertical line. And if I would draw the horizontal line, I would see that in this kind of structure I would have symmetry with respect to a horizontal mirror plane, and in here I do not have, and so forth. And then of course rotations, I may imagine that I'm rotating this lattice with respect to a certain point, and then depending on our basis, what do we have inside each lattice point, we may or may not have rotational symmetries in our structures. So I want to say that the symmetries, they are extremely useful and they are extremely important when we are understanding periodic structures. And this is an understatement. The symmetries are one of the most important things that there are when we want to understand the properties. The trouble is that it's not a trivial concept. It's actually very, very hard to try understanding what happens, and we need to go surprisingly deep into the mathematics and into understanding so that we could really fully start appreciating what symmetries do and do not in our structures. But hopefully, at least you believe me when I say that this is very fundamental and this is very important. But you also need to content yourself by just understanding that a complete understanding will not be formed for you during this course regarding symmetries. It's way too complicated for you to grasp all the subtleties on just after passing an introductory course on the topic. Regarding this course, what we may grasp and what we should definitely understand is that the mathematical description that we have of our piece of a matter, it must exhibit the same symmetries that we have physically in place. So for example, if you're dealing with lattices that have some kind of symmetries, and if you're dealing with functions that are then describing what happens inside such a lattice, that mathematical description must have the same kind of symmetry properties. So for example, if you would have an electron here, the electron must be ignorant to the different directions because these are equal, they are symmetric. Then necessarily is the case that if you have a function that is describing the electron in our lattice, that mathematical description must also have the same symmetries. And this is maybe something that takes a while to think and agree before you can believe it that is the case. But this is something that is very important for you to grasp already now. And we will speak of that a little bit more when we are going into the X-ray diffraction bits and pieces. So this is very important, for example, right away, soon when we are going into the X-ray crystallography, which is a field of science that is being used to characterize and understand crystalline structures. Maybe solids, so crystals, or it may also be biological molecules, so for example different proteins and their three-dimensional configurations. But here we are at the end of our first very lecture. Thanks for listening to me, and please stay tuned. We will in the next lecture go to some example cases of what kind of crystalline structures we may have. Thanks and bye-bye.